Hello, with this video I'm going to demonstrate camera calibration using a Python program tool developed by Professor Vincent's lab. So you can access the camera calibration tool from github.com VIN389 ImproMeasure. So this is the site where you can download the calibration tool. You can download it as a full package from this. So for now, I'm not going to download the calibration tool because I already have in my computer. So let's start the calibration process. So I'm going to open the Anaconda prompt. So this Anaconda prompt helps us to access the main calibration tool by just defining the file path where the calibration tool is located. So the calibration tool located the calibration tool is located in my computer in a local disk. So E first semester. So now we are in the ImproMeasure folder where our calibration tool is located. So we can list the files inside the ImproMeasure folder. So all these files are located in the ImproMeasure directory. So these files are the calibration tool programs. So our main program is this tk calib.py program. So before opening the tk-calib.py, we have to pick pointers from an input image. So to do so, we have to open we have to open a program which let us pick pointers from an image. So let's write Python. So there are two ways or two methods to pick pointers from an input image, PPS and PPT. So I'm going to use PPS. So PPS lets me pick endpointers from an image by mouse, and uh, it saves it in CSV file and image file. So let's write PPS. So the program asks for the file path of the input image. So my input image is in this directory. So this is my input image. But before going to the picking process, I have to say something about this image. So as you can see, this is the Carlton University Shake table. So also this is the imaginary plane drawing by assumptions. So this is we are assuming this is the ceiling. So the ceiling is suspended under the shake table. So as you can see, there are some markers on the surface of this sailing. So these markers are important to detect and track the position and orientation of physical objects in the real world. So the actual sailing uh, must be marked with this high contrast markers. So this is just an assumption, but in the actual demonstration, the sailing must be marked with these high contrast markers because these markers are very useful to detect and track the position and orientation of physical objects in the real world. So they also allow us to track them regardless of the moving object surface. So it's also important uh, for the accuracy of our measurements. So the sailing must be the sailing surface must be marked with this high contrast markers. So let's proceed to our calibration process. So this is my input image with markers on it. So this is the file path for my input image. So this is the file name. I'm just copy and paste the file directory to just to avoid some writing errors. So the program asks for the number of pointers to be picked. So now there are 20 pointers which need picking. So there are 5 on the x-axis, 4 in the y-axis, so total 20. So I'm going to write 20 points. I have 20 points. So then the program asks for the output file. So I'm going to save in the same directory as the input file. Picked points. Picked pointers .csv. Then the program asks for the output image. So I'm going to save in the same directory. Picked pointers .jpg. Enter. So now we are going to start the picking process. So I have 20 pointers. So the first point to pick is point 1. So I have just enter 1. So this is my point 1. Then this is the z axis, this is the x axis, and this is the y axis. in the world coordinate. So this is x, this is 0.1. You can zoom uh, the ROI by just pressing enter. So as you can see, you can zoom it here. So this is the center point. So when you done zooming, you can press escape. So 0.2, this is 0.2, then 0.3, this is 0.3, 0.4. The procedure is the same for all points. Just entering the point number, then selecting ROI. now we are in charge 20 pointers. So to finish, we have to press 0, enter. So our picking is completed. So let's see our output files. So these are the pointers picked. So these are the coordinates, the image coordinates. Sorry. So now we can open the main program, calib. So the calib main program has the graphic user interface. So this is the box where the world coordinate is going to be filled with world coordinates. Also, this is the image 2D coordinates. We have just saved our 2D image coordinates in a CSV file from the peak points process. So let's copy and paste the world coordinate. This is the assumed world coordinates. So this is also imaginary. So all the we assume the sailing is horizontal. So the coordinate of z is at 2600 millimeter. So this is x, this is y, and this is z. So let's copy and paste it to the calibration tool. Copy, Control V. So this is the world coordinate. Also, let's copy and paste the image coordinates. Also, these are the image coordinates. Copy, Control V. So these are the image coordinates. So let's select the calibration image. So this is our calibration image. So our image has a size of 800 by 641. So let's guess the camera matrix. Let's delete this. So to guess the camera matrix, we have to understand some mathematical relations of the camera matrix parameters. So let's see this image. So if this is a camera, so So this is the viewing direction to the x and y axis. So this is the image. So this is the width of the image, and this is height of the image in pixels. So if we take this one, this AD, so it is like this. This is A, and this is D. Then this is the field of view, and this is 6. This is 6, and this is fx. So if we assume this angle is 90 degrees, so this line bisects uh, line AD into the same distance. So if this is 45 degree, so fx and cx are the same. So if fx and cx are similar, so in here cx is 800 pixels. It is the width of the image. So over 2, so it is 400. So cx is 400, so fx is also 400. So half of 800 is 400, 0, 400. Enter. So cx is half of the pixel width, so it is 400. Then 0 fy is, if we let's assume it is the same or similar with fx, then cy is half of the height of the image in pixels. So the height of the image is 641 pixels, so half of 641 is 320.5. Then 0, 0, 1. So this is our initial guess. This is our initial guess. So let's leave the distortion coefficient as it is. So we have also to put it off this fix. So let's calibrate it. Yeah. So these are the projected coordinates. These are the projected errors. So This is the rotational vector, the translational vector, the camera matrix. This is a distortion coefficient. So this is the camera uh, position. So see, the camera position is 2.3 meters to the right. So I think it makes sense. So this is 0, 0. So the camera is the x-axis, in the x-axis direction is around the center of the shake table, and the camera is 21 centimeters to the negative y-axis. So as you can see, this is the footing of the shake table. So the camera is not far uh, from the shake table, so it makes sense. So 20 centimeter to the negative y direction. This means positive y direction is to this. So the camera is almost 20 centimeters behind the shake table. Then the height of the camera is 5.7 meters. So this doesn't make sense. So let's see the drawn pointers. So these are hard-picked pointers, and these are the calculated pointers. So the yellow is the calculated, and the green is the picked. So I think it's very good because most of the points are precise. Then assume that this is consider that this is an imaginary plane. So this is how the TK calib tool calibrates the image. So we can draw undistorted pointers. Let me save this one. Okay. Yeah. So these are the undistorted point drawing. So from the image, this line originally this line was a straight line. Now you can see it is distorted. So this is just the corrected image or the rectified image. So this image is free of distortions. Also, we can draw some grid lines to see how much the image was distorted. So let's draw at 300. So let's save the camera parameters as a CSV file. So this is a CSV file. CSV. So this is the exported camera parameters. So this is the image width. This is the image height. This is the rotational vector, and this is the translational vector. Then this is fx 0 cx 0 fy cy 001, and this is the distortion coefficient. So this is the image, the camera location. So 2.3 meters to the right, almost at the center of the uh, shake table, and this is the location of camera in the y direction. It is 20 centimeter behind of shake table. So this is the camera height. I think it's a little bit exaggerated. So, but the x and y coordinates are, I think, it makes sense. So this is how we calibrate our image. Okay, thank you. This is all about how we measure and calibrate our cameras. Thank you.